Welcome to this video tutorial, one of many in a series designed to get you up and running with Leapfrog. This video is part 3 of 4 discussing basic geological model building. In the previous video, I introduced the different surface types available in Leapfrog and how they interact with one another. In this video, I will show the new Intrusion style surface, and I will also show how Leapfrog creates volumes from these surfaces. I'm going to be demonstrating these tools using two separate examples in Leapfrog. In the first, I'm going to be dealing with a data set that contains 3 units: the quartz porphyry, the granodiorite, and the miscellaneous sediments. Given what we learned in the last tutorial, I'm going to use the Intrusion tool to build the quartz porphyry and the granodiorite surfaces. When you're building intrusions, it is important to build the surfaces from the youngest to the oldest. In this case, the quartz porphyry is the youngest unit that came in and cross-cut everything else. The reason for building youngest to oldest in the case of a cross-cutting intrusion is based on how Leapfrog creates surfaces and volumes. If we take the example of building the quartz porphyry, or the QZP, we build this surface by taking the contact points between it and all of the other surrounding units that exist at the time of its emplacement. Now, let's see how this is done in Leapfrog. We start by right-clicking the surface chronology, New Intrusion. We can see there are several different data types we can use to build this new surface, but in this case, we're going to select Base Lithology. The interior lithology is our unit of interest, and in this case is our quartz porphyry. As I mentioned, we want to make contact points between the quartz porphyry and all surrounding units, as it's the youngest unit. So we're going to leave the granodiorite and the miscellaneous sediments in the exterior lithologies, and therefore a contact point will be created. Once we're happy, we can click OK, and Leapfrog will create our new surface. We can see that this surface accurately represents the data shown in the drill holes, but it isn't necessarily a nice looking surface. We can see it contains lumps and bumps, and it isn't as smooth as we would expect. We can refine the surface using a number of different techniques, but the first and easiest is to simply set a trend. However, before we set a trend, I'm going to ensure that we are actually snapping this surface to the drill holes. If we turn on the edges for this surface right now, we can see that we're getting really close to the contact points, but it's not snapping right to that point. To snap a surface to the contact points, simply double-click this upper level folder and select Snap to Data, All Data, and click OK. As you can see, Leapfrog's now recreated the surface and is now snapping that surface using triangle vertices to all of the contact points. Once we're happy with the snapping, we can now look at modifying this surface by applying a global trend. For a simple trend, we can use the plane tool in Leapfrog to define a plane which will give us a dip, dip azimuth, and pitch. To assign a plane, orient the scene until you're looking straight through the quartz porphyry segments. To make it a little bit easier, I'll make the surface invisible and I will view just those quartz porphyry units. I can rotate so that I'm either looking a long strike or down dip of the unit of interest. The goal is to be able to draw a plane approximately through the middle of the unit. If you're not happy with the alignment of the plane, you can simply click onto it and use the toggles to modify, or just draw a new plane. You'll notice on the plane there's this green arrow that you can move in a 180-degree space. This green arrow represents the pitch direction, and the pitch direction of the plane represents the maximum trend direction. The intermediate trend direction that we're going to talk about is perpendicular to the pitch, but still within the plane. And the minimum trend direction is perpendicular from or out of the plane. Now that we've defined our plane, which will define our trend, we need to tell Leapfrog to apply the dip direction, and pitch of the plane to our quartz porphyry intrusion. To do so, double-click on the quartz porphyry surface in the project tree and then click on the Trend tab. To apply the values from the plane to the quartz porphyry surface, click the Set from Plane button, and this will copy the parameters of the plane across to this surface. The amount of stretch that is applied along each trend direction, the maximum, the intermediate, and the minimum, is defined by these ellipsoid ratios. By default, they are set to 3, 3, 1, which means the surface will be stretched 3 times more in the direction of the plane than it will out of the plane. Let's now take a look how this has modified our surface. In this case, you can see that these ellipsoid ratios did a pretty good job of stretching the surface so that it looks geologically reasonable. But if you didn't want as much stretch, you could easily drop the maximum and intermediate values down to 2 or 1.5, and it would still add a trend to the surface. It just wouldn't be as strong. This is obviously a simple approach for dealing with a simple trend. Frequently, trends are not this simple. They bend and fold in XYZ space. For instances which cannot be dealt with by a simple plane, Leapfrog has the Structural Trends tool. Information about structural trends can be found on the Leapfrog blog and also in the help files. Also, a basic introduction will be covered in a different video. Now that we've completed the quartz porphyry surface, we will follow a similar process to model the granodiorite as we did the quartz porphyry, with a few key differences. So we'll start by right-clicking Surface Chronology, New Intrusion, from Base Lithology. The main difference in building the granodiorite surface is that it's an older intrusion, so when we're deciding which lithologies to ignore, we should choose to ignore the quartz porphyry surface. This means that when Leapfrog extracts contact points, it will only be finding points where the granodiorite surface contacts the miscellaneous sediment lithology. This is important because when the granodiorite intruded, the quartz porphyry didn't exist, so we don't want the granodiorite to be controlled by any contact points with the later quartz porphyry intrusion. This is something to keep in mind whenever you're building a series of intrusions. You will always want to ignore the younger lithologies so those contact points are not created another time. Now that we've built the granodiorite, let's take a look at the intervals that were actually used to create it. Just like in the last example, we can use a plane to modify the orientation of the granodiorite surface by selecting the plane, double-clicking the surface in the project tree, hitting the Trend tab, Set from Plane. In this case, I'm going to use smaller values for the maximum and intermediate directions and see how that affects the surface. One important thing to keep in mind when building surfaces in a geological model is that you always build one fewer surfaces than you have units or desired output volumes. In every case, your final unit will be defined by whatever is left over when you've built the last surface. In this case, we've defined the quartz porphyry and the granodiorite, and while building those surfaces, we've already made all the necessary contact points with the miscellaneous sediments. Ultimately, anything in this model that doesn't sit within either of these two built surfaces will be the miscellaneous sediment unit. So we don't need to build a specific surface for that. You'll see what I mean by this in a minute. The last thing I want you to notice before we build the volumes from these surfaces is that the inside of the surfaces match the color of the unit that they're being built around. You can see that for the granodiorite as well as the quartz porphyry. The outside of these surfaces are currently the unknown color given by Leapfrog, because at this point Leapfrog doesn't know what sits on the outside of either of these surfaces. Now we're ready to create the volumes. You'll notice that right now the surfaces are cutting through each other and they look a little bit odd, but this will all be taken care of when we build volumes from them. To activate the surfaces to create the volumes, double-click Surface Chronology. The most important part of this step is to ensure you have the correct cutting relationships for the surfaces. If you know the age relationships for your units, that's great, and you'll want to have them placed youngest to oldest in the list. In this case, we can see the quartz porphyry was younger than the granodiorite, so I moved it up the list. What Leapfrog will do when creating the volumes is take your initial volume space defined by your model extents and your topography, and use the surfaces to carve pieces out of that volume. The surface at the top is the youngest or has the highest priority in the cutting relationships, and that volume will be created first, and then the next surface will be created from the volume that was remaining. As you move down the list, eventually you will be left with one final volume that in this case hasn't yet been defined. To see that, let's create the volumes. To actually activate the volumes, tick the boxes and click OK. Leapfrog will process the cutting relationships I just mentioned and leave us with airtight interlocking volumes. The way that Leapfrog creates volumes, it's essentially impossible to have any overlapping triangles or crossing triangles or spaces left in the model. Now that the volumes are created, let's take a look at them. There'll be 3 volumes: the quartz porphyry, the granodiorite, and an unknown. So far we've defined the interior of the 2 intrusions, but not the exterior miscellaneous sediments. To define the exterior, double-click on the second oldest unit in the model, which in this case is going to be the granodiorite intrusion surface. We can see right now that the first lithology is granodiorite, but the second lithology is defined as unknown. We know in this case the only thing older than the granodiorite is the miscellaneous sediments. So when we set that and click OK, we can see the outside color of our second oldest unit becomes the color of the sediments, and the volume is now created to be the sediments. Now that the geological model has been created, we need to check that it accurately represents the data shown in the drilling. One of the best ways to do this is by looking at both the geological model and the drilling at the scene in the same time and creating a slice. I can choose to unfill that slicer so that I can see the drilling and the geological model at the same time. In the next video, I will talk about building a new deposit and a new vein style of surface.